Here we have the logistic equation. dp dt equals this expression here, where n is the limiting condition or carrying capacity. Sometimes the logistic equation is written in a different form, such as this one here, where k is the limiting condition. Unlike an exponential curve that increases forever, this equation is a more realistic model for population growth, since lack of food and other resources can restrict population to a maximum level. So here it's like, when you have a look at the curve, it increases like an exponential curve, but then it levels off to this limiting condition. If you have a look at example 15, Josh sets up a new salmon farm with 250 fish. The differential equation for P, the population of fish, is given by this expression here. Now this expression is like this expression here set up in the same form, where n here is 1,000. So that will be our limiting condition or carrying capacity. Part A wants us to show that this expression is equal to this over here. Now I'm going to start with the right-hand side, and then I'm just going to keep my 5 on 12 outside the bracket, have a common factor in the denominator, and add these two fractions. When I do that, I'm left with 1,000 minus p plus p over this common denominator. I can then simplify that to that expression here by just minus p plus p on the numerator, and then to multiply the 5 over 12 into the bracket, I get 5,000 over 12p outside of 1,000 minus p. Now, because 12 on 5,000 is equal to 0.024, I can say that 1 on 0.024p is outside of 1,000 minus p, which is what we're trying to prove, which equals the left-hand side. So, in example B, we want to use that result that we've got in part A to show that the salmon population is given by the equation here, where P equals 1,000 over 1 plus 3e to the minus 2.4t. Now, we're going to start with our original differential equation. dp dt equals this amount here, this expression. To start with, I'm going to find dt dp, and that is 1 over this expression. And therefore, I know that t is going to equal the integral of this expression, dp. Then from part A, I can rewrite that in this form here. So, and then I'm just going to perform that integration, firstly taking 5 on 12 outside the integral, and then that will equal 5 on 12, the absolute value of log p, natural log of p, minus the log of 1,000 minus p, plus c. Using our log laws, using this subtraction here to our division, so we get 5 on 12 multiplied by the natural log of the absolute value of p over 1,000 minus p plus c. Now, I can just change the subject of the formula to p, but to do that, I've now got this equation t equals 5 on 12, the natural log here of p over 1,000 minus p, absolute value, plus c. I'm just going to multiply both sides by 12, divide by 5. I've subtracted the t of minus the c just to get this expression here. I know that that's just 2.4 to get this expression here. And now I've got, using our logarithm and exponential definition, we can rewrite this here as e to this power 2.4 of t minus c equals this expression here. Therefore, we've got e, when I expand out that bracket, e to the power of 2.4t minus 2.4c equals this expression. 2.4 times 2.4 is 4t, 4 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 times 2.4 is 4t, I know that I can rewrite that using our index laws. This here, I can write that as this expression here. And I'm just going to rewrite this left-hand side such that this here is a constant value because I've got a constant value C multiplied by 2.4 multiplied by E, which is a constant value. So I'm just going to rewrite this here where A equals this amount here. So I've got A e to the 2.4 t equals P over 1000 minus P. I know that I want to find A. And to find A, I've note that the initial population is 250 in the question. So when I substitute into my formula, I get this here, t equals 0 and p equals 250, and I've just substituted that into my formula so that I can get A is equal to 1/3. And so from my original, from where I worked out this value here, A e to the 2 point, sorry, I'll put that on the screen. So from this that I worked out on the previous page, A multiplied by e to the 2.4t equals this expression. I can say that A is, because A is a third, I can now write it like this. If I just multiply both sides by 3 and also 1000 minus P, I get this expression here. To this line here, I've just multiplied this, divided by this amount here, e to the 2.4t, and therefore I've got 1000 minus P equals this. Add P to both sides to get this. And now all I need to, I've now got the 1000 equals P plus 3P e to the minus 2.4t, which equals this when I take out P as a common factor. And therefore I can just say that divide both sides by this amount, P is equal to 1000 over 1 plus 3e to the minus 2.4t, which is what we were trying to prove. Before I go any further, part C is very straightforward, and I think you can read through the textbook to see how to solve part C, but I did want to have a quick look at part D. Now, part D says, what is the maximum possible population of fish for Josh's salmon farm? Now, when we have a look at our original equation, P equals 1000 over 1 plus 3e to the minus 2.4t, we know that as t approaches infinity, as time goes on and on, as t approaches infinity, this expression down the bottom, 3e to the minus 2.4t, will approach 0. So this expression in the denominator will equal 1, will approach 1, and therefore P will approach 1000 because we'll have 1000 over 1, and so the maximum number of fish is 1000.